uh, is there any disturbance in my voice, or is it clearly audible?
Yes, sir.
It's clear. It's clear.
Okay, thank you. Thank you. All right. So let me share the file. So is it visible? This presentation is visible to everyone?
Yes, sir.
Yes, sir.
Okay. So in the last class, what we started looking at is uh, how we can, analyze the heat transfer when there is a conduction and convection together, isn't it? So for a flat geometry, what type of equation we are expected to get, and when we are having the cylindrical geometry, what type of equation we are expected to get, that we have derived. So what we concluded that in both the cases, when we have convection and conduction both are occurring, and such situations are regularly seen in the process application, isn't it? Because very often the heat transfer is taking place between two fluids, and obviously we don't want it to mix these fluids, so that means it will be separated by a metal wall, isn't it? So clearly conduction and convection occurring together, this type of situation regularly seen in a process application, isn't it? So when we are assuming that both the fluids are separated by a plane wall, then we get this type of equation, isn't it? Q is given as UA delta T, where U is given as 1 by U is given as 1 upon H1A plus 1 upon A KWL plus, sorry, uh, 1 by H1 plus 1 upon Kw by L plus 1 upon H2. That is what the expression of U you are going to get. Okay. Again, here what we said that this U is nothing but the overall heat transfer coefficient. So this overall heat transfer coefficient accounts both convection at both sides of the metal as well as the conduction through the metal. Is it clear? Yes or no? Hello?
Yes, sir.
So again, what we said is, let's say if you are looking at only the convection outside or convection inside, then we are going to use only the corresponding heat transfer coefficient, and that will be small h. So this U, capital U, when this capital U we use only when we are looking at all three together. Okay, so that one has to remember. Then we have seen the cylindrical geometry, and this is what regularly see. In this case, we have looked at the example of this double pipe heat exchanger. So this double pipe heat exchanger will look like this, isn't it? So there is a inner fluid flowing through the inner pipe, and there is a outer fluid flowing through the annular region, and both these fluids are separated by a cylindrical wall in between. So there is a convection inside the pipe, there is a convection outside the pipe in this annular region, and there is a conduction through this cylindrical metal wall. So in such case, what we have seen is we can do the same analysis, and after doing that, what we get is we get this equation Q equals to U naught A naught Ti minus T naught, or Ui Ai Ti minus T naught. So here you can see that the equation Q can be represented in terms of overall heat transfer coefficient, which is defined in terms of outer surface area, then we call it as a U naught. If it is defined in terms of the inner surface area, then we call it as a UI. Okay, isn't it? And the expression for U naught and UI are given here. Is it clear? Is it
Yes.
clear to everyone? Hello, this part. Is there any question so far?
No, sir.
Okay, so then based on this, we have seen one problem, isn't it? In this problem, we have just found out the characteristic dimension, which is volume divided by area, and then we have calculated this Biot number, and then the Biot number is very less than 0.1. So based on that, we are assuming that the internal resistance is negligible, and based on that, then we have obtained the time in this particular problem. Okay. Okay, so let's extend our analysis to the new system. So here we are going to look at the heat transfer from the extended surfaces or fins. So this type of extended surfaces you regularly see in if you are driving a car, driving a bike, you can see your bike engine outside there is some corrugated surfaces are there, isn't it? Have you all seen that? Some corrugated surfaces are there outside your engine, outside the engine of your bike.
Yes, sir.
Similarly, you will see that in a computer also, to have a higher heat transfer, you will see that some corrugated surfaces are there inside the computer. Okay, so why we in general have such extended surfaces? Why we have such extended surfaces? So the reason behind this is, very often what we want is we wanted to have a faster heat dissipation to the air. Faster heat dissipation to the air. So in this case, you can see that this is the wall. Let's say this is the wall. We wanted to have a dissipation of the heat from this wall to the ambient. Okay, but clearly ambient is comprised of what? Air, and air being a gas, its thermal conductivity will be much lower compared to this metal wall, isn't it? So that means how much heat is being transferred by a conduction to the surface, only the part of that will get dissipated. So rate of heat dissipation outside will be very low, isn't it? So your rate limiting case basically becomes the gas film outside here. Do you all agree? Yes or no?
Yes, sir.
So now the question which we are asking ourselves is, can we do better than this? Can I increase the heat transfer to the air by doing something? So reason is, see, here the heat dissipation outside the ambient will be done by what? Will be characterized by what? Newton's law of cooling, isn't it? So that is given as HA delta T, isn't it? Where H is the heat transfer coefficient, which accounts the resistance to the heat transfer, convective resistance, isn't it? It accounts the convective resistance. So I have very little flexibility in increasing the convective resistance unless I add the turbulence or do other things, isn't it? That is one way of increasing the H. But I can also increase the area of convective heat transfer, isn't it? And I can have the same amount of heat transfer. Do you all agree? Isn't it?
Yes, sir.
So either I can increase the value of H, because heat dissipated to the air will be given by what? HA delta T. Delta T is fixed. Ambient temperature is fixed. Surface temperature of the wall is also fixed, isn't it? So delta T, I do not have any flexibility to change at all. So only two factors are there with me. Either H I can change, or either I can change A. H I can change by increasing the turbulence, isn't it? But that will account some energy, isn't it? Some because mechanical pump you need to add, so you will have some cost with respect to that. So probably you don't want it to have that, isn't it? So the only flexibility you have is, can I increase the area of heat transfer? And I can increase the heat transfer area by having such extended surfaces. So can you see the point why extended surfaces are so important?
Yes, sir.
Is the perspective clear to everyone why we are studying this? Hello?
Yes, sir.
And you see this type of extended surfaces in all several heat transfer equipments, like the example I have given. If you look at your bike engine, you will see these fins protruding outside of the engine, isn't it? So that we see regularly. Is it clear to everyone? Yes or no? Hello?
Yes, sir.
Okay.
Yes, sir.
So let's look at a very simple case. Okay, there are different types of fins are possible. We can have a cylindrical fin, we can have a triangular fin, we can have all sort of geometries are possible for an extended surface. But for a time being, let's take a this rectangular fin as shown here. So there is this rectangular surface is protruding outside of this wall. My aim is to have a faster heat dissipation from this base wall, which is there on the left hand side, isn't it? So by increasing this extended surface area, I will have a more heat dissipation by a convection, and because of that I can cool this wall much faster if I don't use the extended surface. Okay, isn't it? Compared to if I don't use this extended surface, with this extended surface I can cool this surface, this base surface, much faster. Do you all agree? Hello?
Yes, sir.
Okay. Now let's look at the geometry. So this extended surface is having this length L, ambient temperature is, let's say, T naught. Again, this breadth of this particular rectangular fin is B, and width of this rectangular fin is W. And we are looking at the distance from this particular edge. So as we move along this direction, the X is increasing. So X is the distance we are looking at from this base. Okay, and the temperature of the wall is TW. Is it clear? At least the geometry is clear.
Yes.
Now in this case you can see that in this extended surface the convective heat transfer takes place from this top surface. It can take from the bottom surface. It can take convective heat transfer can take place from this particular end here. Also it can take convective transfer can take place from this particular side. There are two such sides, isn't it? Do you all agree?
Yes, sir.
But another assumption what we are taking here is we are assuming that this width of this fin is very small. So width of this fin in a transverse direction, that means vertical to down, this width is very small. So why that assumption is important? When we are saying that this width of this particular rectangular fin is very small, that means that we can safely assume that the internal resistance is minimum. Do you all agree? Is negligible, and the uniform temperature is along the transverse direction. Can I assume that? Yes or no?
Yes, sir.
Isn't it? So if I take this width very small, in that case the characteristic dimension will be very small. If I calculate a Biot number, that will be Bs by K. That Biot number will be very small compared to 0.01, and we can assume that there is no temperature gradient along the transverse direction. So if I take any cross section here or here along the transverse direction, that is vertical to down, your temperature is constant along the transfer direction, but temperature is going to vary along the longitudinal direction. So as I move from this base to here, at this end, my temperature is going to vary, but my temperature is not going to vary from top to bottom. Do you all agree?
Yes, sir.
Does it make sense what I'm saying to everyone?
Yes, sir.
Okay. So now, as I said, here this temperature is going to vary. This temperature is going to vary as I move from this base end to this up to this, end here. My temperature is going to decrease because my convection is going to take place from this surface, and as the convection is taking place, my temperature here along the longitudinal direction is going to decrease as I move from x equals to 0 to x equals to L. Do you all agree?
Sir.
So that means if my temperature of this extended surface along the longitudinal direction, that means along this x direction, is decreasing, that means my driving force delta T. What is driving force in this case? Any location here, my driving force will be what? The temperature, actual temperature at that location in this fin minus the ambient temperature. That will be the driving force, isn't it? That will be the driving force in that case, isn't it? Do you all agree? And that driving force is decreasing as I am moving along the longitudinal direction. So that means what? That means what? My heat flux is also varying as I am moving along. Do you all agree?
Yes, sir.
And when my heat flux is not constant, even though I am looking at the rectangular surface here, but my heat flux is not constant across the length. If I'm moving from one length to the another, my heat flux is not constant. It's changing. It is changing. That means what? I need to do a shell balance. Does it make sense to everyone?
Yes, sir.
Yes, sir.
Because my small qx is going to vary along the longitudinal direction. That means I need to make a shell balance here. That's what we take it in a cylindrical geometry also, isn't it? That QR is varying along the radial direction. That small QR is varying along the radial direction, isn't it? That's why we make a shell balance there. So same argument I am making here. Does it make sense to everyone?
Yes, sir.
Okay. So now, as I am saying that we need to make a shell balance, let us assume a small shell of thickness delta x at a length x, isn't it? From this base end. Okay, this delta x is the width here. So what will be the heat transfer area? What will be the heat transfer area? Heat transfer area will be the cross-sectional area, isn't it? Isn't it? So cross-sectional area in this rectangular fin will be what? B into W. Do you all agree? Do you all agree with this? Yes or no? Remember,
Yes.
along this horizontal direction, your heat is will be transferring, isn't it? So the heat flux will be along this direction, isn't it? And then the heat dissipation is going to take place from the surface. That we will account later. But the heat conduction is along the longitudinal direction, and the cross-sectional area for the heat conduction, I am saying heat conduction. See, there are two heat transfer taking place. One is the heat conduction through this extended surface, and another is heat convection from this outside surface, isn't it? So for a heat conduction, what will be the surface area? Cross-sectional area of this rectangular film. And cross-sectional area in this case is going to be what? B into W. Yes or no?
Yes, sir.
Okay. So now what will be the rate of heat input at X? Rate of heat input at X will be cross-sectional area BW into heat flux QX at the location X. Similarly, rate of heat output, heat output, there should be output here. Okay. So is my slide are still visible?
Yes, sir.
After changing this?
Yes, sir.
Okay. Okay. So what we are saying is the rate of heat output at X plus delta X will be BW, that is the cross-sectional area. So cross-sectional area is going to remain same as I'm taking here or here, doesn't matter, because cross-sectional area is BW, is going to be same for conduction, isn't it? So my rate of heat output by conduction here in this rectangular film is going to be BW into QX at X plus delta X. Is it clear to everyone? Correct. Now, in addition to rate of heat input to this shell and heat output to shell, again from this surface which is outside here, isn't it? There is a heat dissipation is taking place to the ambient, isn't it? And what will be the area for the heat dissipation here? What will be the area? All these areas surrounded here, isn't it? Do you all agree?
Yes, sir.
Sir. Yes.
So that will be what? That will be what? 2B, isn't it? And then 2W, isn't it? 2B in plus 2W into delta X, isn't it? That will be the area, isn't it? So we are looking at this all shaded area, which will be the heat transfer area for convection. Remember, these two terms are, we have to carefully use this. In the first case, I am saying the heat transfer area for conduction. So that will be the cross-sectional area here. Okay, and here, and both the cross-sectional areas are going to be same. But when we are saying the heat transfer area for convection or heat dissipation, that will be this area which is shown by a shaded part here, isn't it? So that will be 2b plus w into delta x, because 2b plus w is going to be the perimeter, and that perimeter multiplied by the thickness of this width of this thickness of this the shell which we have assumed delta x, isn't it? So is it clear to everyone? Does it make sense what I'm saying?
Yes, sir.
Yes.
So that will be the heat transfer area for convection. So now rate of heat input we have obtained, rate of heat output we have obtained. Again, there is a rate of heat loss also taking place to the ambient, isn't it? From the exposed surface, isn't it? So that will be given by what? This area P delta x into heat transfer coefficient minus delta T, multiplied by delta T, isn't it? So T minus T naught. So T is the temperature at any location X, isn't it? So this is nothing but HA delta T. Do you all agree?
Yes, sir.
Yes, sir.
And there is no accumulation. We are not looking at the unsteady state heat transfer. We are not looking at generation, isn't it? So our shell balance will be what? Input minus output, and there are two output terms here. So both are subtracted here. So BWQX at X minus BWQX at X plus delta X minus P delta X H T minus T not equals to 0. And I can divide this entire equation by BW delta X. So if I divide this entire equation by BW delta X and take this P delta X H T minus T naught on the other side, what I'm going to get is minus D by dx QX equals to PH by BW T minus T naught. Is it clear to everyone? Equation number
Yes,
1.
sir.
Yes, sir.
Yes.
Okay. Now we have obtained the equation for the heat balance. Now we wanted to solve it, isn't it? So of course we need to make some boundary conditions to solve this differential equation, to find out how my temperature is going to distribute along the longitudinal direction. Remember I said there is no distribution of the temperature along the transverse direction, but there is a distribution of the temperature. There is a variation in the temperature along the longitudinal direction. So that is what we are interested to find out. So this is what the equation we had. Now let's simplify this equation a little bit. So this QX is a heat flux. We can write this QX heat flux in terms of the Fourier's law of heat conduction as minus K dt by dx, isn't it? Correct. And also we can represent this T minus T naught as a T bar, let's say T bar. And PH by BW we are representing by another variable, let's say zeta. So zeta is given as under root of PH by KBW. So that is nothing but PH by KBW is zeta square. Okay. So with this new notation, I can differentiate dt bar by dt. That will be just dt by dt. So I can just put this dt by dt as dt bar by dt bar by dx, isn't it, directly? So if I differentiate this this equation of T bar, which is given as T minus T naught with respect to X, what I'm going to get is dt bar by dx, and that is same as dt by dx. So I can replace this, isn't it? So with this substitution of all these variables, new variables, what I get is this square T bar by dx square is equals to PH by KBW, which is again replaced by zeta square T bar. Do you all agree?
Yes, sir.
This makes sense to everyone?
Yes, sir.
Yes.
Yes, sir.
Okay. So now let's look at the boundary conditions. So what are the boundary conditions? The first boundary condition is at X equals to 0, my temperature is going to be TW, because that is what the base temperature is. Wall temperature is going to be TW. Do you all agree? Yes or no?
Yes, sir.
And when X equals to L, then I am saying that when I am taking at this particular element, my heat transfer is taking place only along the circumferential direction, isn't it? But when I reach to this particular end, this additional edge becomes available to me for heat dissipation. Do you all agree? When I reach to this end, this is the additional edge I am having for dissipation, isn't it? In terms of if I'm looking at the shell balance, correct?
Yes, sir.
Yes, sir.
Yes,
So
sir.
here my boundary condition will be what with respect to this? So boundary condition will be what when x equals to L, my heat flux here will be whatever the convective heat flux I am going to have, isn't it? Does it make sense? So I will have minus k dt by dx will be equals to HA delta T here. Sorry, H delta T here, isn't it? At this end. Do you all agree? So that is nothing but convective boundary condition. Do you all agree?
Yes, sir.
Isn't it? So that is what we have written. Of course, this is a complex case we are solving, but there is a very simple case also is there when people look at solving the fin problem. But that also we will see in a subsequent slides. But for a time being, let's start with the complex case. So complex case is my another boundary condition is going to be the convective boundary condition. So that is my heat flux will be same as the convective heat flux at the x equals to L. So at x equals to L, minus k dt by dx will be given as h t minus t naught, and that is given as minus k dt bar by dx is equals to h t bar. Do you all agree?
Yes, sir.
And at x equals to 0, t equals to tw. So that means this t bar will be what? Tw minus t naught. That is what we have defined t bar, isn't t minus t naught. So t is replaced by tw. So this becomes tw minus t naught. So both these boundary conditions are clear to everyone? Yes or no?
Yes, sir.
Yes, sir.
Now this is what the equation we have started with. This is the equation, final equation we had. D square t bar divided by dx square is equals to zeta square t bar. Similar equation which we have seen for the two-dimensional heat conduction earlier, isn't it? There we have solved the individual equation for two cases. One was minus lambda square t, and another one was plus lambda square t, isn't it? That's what we have seen earlier,
Yes.
isn't it? So when we are having a plus here, what we get? Exponential terms we get, and exponential terms are hyperbolic terms. Both are same, isn't it? Cos hyperbolic and sine hyperbolic we can represent in terms of e raised to power, zeta x or e raised to power minus zeta x, isn't it? So it doesn't matter. This is just a representation. Is it clear to everyone? So we can get the analytical solution of this equation as t bar as c1 cos hyperbolic zeta x plus c2 sine hyperbolic zeta x, and then we wanted to apply the boundary conditions. So far everything is clear to everybody? Hello?
Yes, sir.
Does it make sense to everyone?
Yes, sir.
Sorry, just a minute. Okay. Okay, so all right. So in this equation, let's put the boundary condition. So what is the first boundary condition? At x equals to 0, we are getting this t bar as tw minus t naught. So we can put that tw minus t naught is again x is 0. So if I put x equals to 0 here, both these terms become 0. So what we get is c1 equals to tw minus t naught. Is it clear to everyone? All right.
Yes, sir.
And then again, let's apply the second boundary condition. So for second boundary condition, we have to differentiate this equation first with respect to x. So let's differentiate this equation with respect to x. So after differentiating, what we get is c1 zeta sine hyperbolic zeta x plus c2 zeta cos hyperbolic zeta x, and then we are multiplying minus k here, and this minus k dt by dx should be equals to what? H t bar. So h multiplied by this t bar. So that is what we have equated here, isn't it? So minus k dt by dx, dt bar by dx is equals to h t bar. This is what we have written here by simplifying or differentiating this equation. Is it clear to everyone, this part?
Yes, sir.
And again, we have replaced here x by L. Remember, this is valid only at x equals to L. So we have replaced here x by L. So this is what we have obtained at x equals to L. Now, from this equation, we can rearrange this equation and we can calculate C2. And C2 comes out to be minus C1 k zeta sine hyperbolic zeta L plus h cos hyperbolic zeta L divided by k zeta cos hyperbolic zeta L plus h sine hyperbolic zeta L. Okay. So now again, if you rearrange this equation by dividing k zeta, what we get is minus C1 into sine hyperbolic epsilon zeta L plus h by k zeta cos hyperbolic zeta L divided by cos hyperbolic zeta L plus h by k zeta sine hyperbolic zeta L. So this is what we have obtained as a C2 just by rearranging this equation. Now this C2 and C1 both we can put it in this original equation. Remember C1 we have obtained. So C1 we can put it here, and also we can put the C2 here, and then we can rearrange the equation. So after rearranging the equation, what we get is this. T minus T naught divided by TW minus T naught is equals to cos hyperbolic zeta L minus x plus zeta by k zeta, sorry, h by k zeta sine hyperbolic zeta L minus x divided by cos hyperbolic zeta L plus h by k zeta sine hyperbolic zeta L. So this final expression we have obtained by putting this C2 expression of C2 and C1 both in this equation 5. So here C1 we have put and C2 we have put. So remember, this C2 also has a C1 term. So that C1 we can take that C1 common. That's why this TW minus T naught term is coming in the denominator. That's what this TW minus T naught is coming in the denominator. Can you see here? Also,
Yes,
sine and cos term you can collect together, and that can be written as this, isn't it? You can expand so that expanded terms you can condense into this individual terms. Is it clear? Hello? Remember, we are having the sine and cos term in terms of zeta L here, but in the original you will have this zeta x term, isn't it? So if you rearrange everything, you will see that you can collect the cos and sine terms, and that will be represented in terms of this cos hyperbolic zeta L minus x plus h by k zeta sine hyperbolic zeta L minus x, and denominator will be same as cos zeta L plus h k zeta sine hyperbolic zeta L. So this is just a simplification after doing the trigonometric manipulation and also putting C2 and C1 directly in this equation 5. Is it clear to everyone? Hello?
yes, sir.
Yes, sir.
Now this equation gives me what? This equation gives me how my temperature is going to vary along the longitudinal direction L, isn't it? Correct. So if you put here, L equals to L, you will get some value, isn't it? If you put x equals to 0, you will get some value, and you can see that the temperature is going to decrease as you are moving from base from the base to the other end at x equals to L. Okay. Again, the heat flux is also decreasing along the longitudinal direction. All right. Is it clear to everyone?
Yes, sir.
Now the question we are asking, so okay, here equation 8 is giving me only the temperature distribution, but I am asking you another question. How much heat will be added to the fin itself? How much heat is added to this entire? Remember, along this length, some heat is getting dissipated by convection, some is being transferred along the longitudinal direction. But the question I'm asking, how much heat is at the first place is given to this extended surface? How much heat is coming to this extended surface? So we can find out that by multiplying area into heat flux at x equals to 0. Do you all agree? So I can find out heat flux exactly at this base end here by putting x equals to 0, and then I can multiply area. So that will give me the total amount of heat that is being added to this extended surface at this base. Do you all agree?
Yes, sir.
Yes, sir.
So this is what we are calculating here. So the rate of heat transfer Q will be cross-sectional area into heat flux at the fin base. So heat flux at the base will be given by what? Minus K dt by dx at x equals to 0. And what will be the cross-sectional area? Cross-sectional area will be again BW, isn't it? Here. So that's what we have written, BW minus K dt by dx at x equals to 0. Now this dt by dx we can directly obtain from this equation. Equation number 8 is the general equation which we have obtained. Now I can differentiate this equation with respect to x. So if I differentiate this equation with respect to x, what I get is this particular bracket. This particular bracket I'm going to get if I differentiate. Remember, this denominator is a constant term, isn't it? This is zeta L. So this is a constant term. I can take it as it is at the denominator, and I can differentiate this numerator. So if I differentiate the numerator with respect to x, what I'm going to get? Minus okay, so cos hyperbolic zeta L minus x is there. So this zeta is there, isn't it? So minus zeta sine hyperbolic again. Okay, so this differentiation we have to carry out. Okay, we can differentiate this and then we can put x equals to 0. So what we are going to get is minus zeta sine hyperbolic zeta L. We will get zeta into cos hyperbolic zeta L minus x. That is what we are going to get. And when we put x equals to 0, what we are going to get is minus zeta sine hyperbolic zeta L. This will be the first term. So only minus sign will be added here, and this x will become 0. And this sine will become a cos, and cos will become sine. Do you all agree?
Yes, sir.
Yes, sir.
So this minus sign get cancelled out. So this is what the final expression which we are getting. Now, whenever we are looking at the fin, so the efficiency of the fin is defined. So efficiency of the fin is defined as actual rate of heat transfer. So this Q is nothing but the actual rate of heat transfer. Q is nothing but the actual rate of heat transfer. And this actual rate of heat transfer divided by theoretical maximum rate of heat transfer. What will be the theoretical maximum rate of heat transfer? If I look at this particular fin, remember my rate of heat transfer is decreasing as I am moving along this longitudinal direction, because the temperature along the longitudinal direction here is decreasing, isn't it? But if I maintain the temperature of this film all over this length as a fixed value of, let's say, TW, then whatever the heat dissipation, whatever the heat exchange will be there, that will be the maximum, isn't it? Do you all agree? Heat transfer will be the maximum. Do you all agree or not?
Yes, sir.
Remember here now, whatever the heat being transferred here is the same as heat dissipated outside, and that heat dissipated outside depends on what temperature is along this longitudinal direction, and that temperature is decreasing from this base end to this length L, isn't it? So clearly my heat dissipation is decreasing as I am moving along the longitudinal direction, but I can increase this dissipation of the heat if I maintain the temperature of this fin exactly at TW. But that's a theoretical estimate. That's a theoretical. That's why I'm saying this efficiency is calculated as the actual rate of heat transfer divided by a theoretical maximum rate of heat transfer. Isn't it? Definitely I cannot maintain this temperature as a same here, but I'm assuming that, let's say, if I'm having the temperature along the longitudinal direction as same as TW, I will have the maximum heat dissipation, and then I will divide that maximum heat dissipation to the actual rate of heat transfer. That will give me the fin efficiency. Do you all agree? Does it make sense what I'm saying? Hello? Is it clear or not clear?
Yes, sir. Clear.
So Qmax I can obtain easily because now Qmax is, see, if temperature along the fin, along the longitudinal direction is same maintained at TW, there is no conduction occurring at the fin along the longitudinal direction. Only the convection is taking place outside, isn't it? So convection taking outside will be given by what? PL plus BW H TW minus T naught, isn't it? PL into H TW minus T naught, that we have already seen earlier when we are looking at this elements. But when we are looking at this complete surface for a convection heat transfer, then this surface also comes into the picture, isn't it? So this additional area BW is coming here because of that. This additional area BW is coming because of that. Earlier we have taken, remember here the convective heat transfer is taken by what? P delta X H. So that is nothing but PL H delta T, isn't it? Yes or no? But in addition to that, I am taking plus BW also, because when we are looking at this complete fin, remember here only this element we were looking at. Therefore, we have not taken the surface area in the longitudinal direction here. But when I'm looking at this complete surface, not only it is going to take place from this complete surface, but also from this outer end here. So BW corresponding to this area will also come into the picture. Does it make sense? This Qmax expression?
Yes, sir.
So Qmax will be PL plus BW, that will be the total heat transfer area of the fin multiplied by H into TW minus T naught. Now if I divide these to this actual equation, several terms get cancelled out. So this TW minus T naught will get cancelled out. What we will get is BW K zeta divided by PL plus BW H, and this sine hyperbolic zeta L plus H by K zeta cos hyperbolic zeta L divided by cos hyperbolic zeta L plus H by K zeta sine hyperbolic zeta L. This is what the final expression we are getting for the fin efficiency. Okay. Now, as I said, the problem which we have solved so far is a simplified problem. It's a simplified problem. Okay. But in a real life, it's a complex problem. But there is also a simplified problem. Okay, so when we are looking at the fin, I definitely wanted to design my fin in such a way that eventually as I reach to this longitudinal end here, my temperature should become same as T naught, isn't it? That should be the ideal design for me, isn't it? If all the heat conducted is getting dissipated from this large surface till this end, that's what I'm desiring. Then I can even design as a triangular fin like this, isn't it? I don't need this surface area additionally, isn't it? Because this surface area will not be a significant compared to this upper surface area or a bottom surface area. Do you all agree?
Sir, but you said the maximum heat transfer will
So I
will
will
be
increase
occurring
the
in
length.
TW.
I will increase the length. I will increase the length along this instead of having this width here. Do you all agree?
No, sir. Could you explain it again, please?
Okay. So ultimately, out of all these surfaces, which surfaces are more responsible for heat dissipation? This top surface and the bottom surface. Do you all agree?
Yes, sir.
Anyway, this width will be very small. So whatever the heat dissipation is taking place from this end or the other end, is this side, back side, will be very small. Do you all agree? Isn't it?
Yes, sir.
Correct. So now I wanted to design my fin in such a way that I want the temperature here to reach to the ambient temperature so that there is no dissipation taking place from this end. And if I assume, if I take a length to that particular extent, then most of my heat is getting dissipated from this top and the bottom surface area, because these are the most responsible, isn't it? Do you all agree? And I can make
Sir,
this fin as thin as possible.
Sir, I didn't understand why do we want the T temperature at the end to be equal to T naught?
Because anyway, see, ultimately what we are, see, when this T here will be, remember here temperature is decreasing along. So when I'm saying this temperature here will be T naught, that means what? All the heat which is transferred by this hot wall to this fin is actually getting dissipated till the end. There is no more heat available here, which will, so remember, if I am having some temperature here which is not exactly T naught, that means I will have some film here, isn't it? Additional film here, correct? Responsible for the resistance.
Yes, sir.
Ultimately, I wanted to design a film in such a way that whatever the heat is added here from the base end should get dissipated till I reach to the end of the fin. Then and then only the purpose of the fin is getting served, isn't it? What is the purpose of the fin? Purpose of the fin is all the heat which this base wall is giving should get dissipated till the end here, isn't it? Correct. And that I can have only if I am, increasing the length here, isn't it? I can have a shorter length here. Okay, then what will happen? The temperature here will be higher. It will not be T naught. Do you agree?
Yes, sir.
And I can
Yes, sir.
increase this. Okay, with this structure, with the same structure itself, I can increase the length of the fin, and I can increase till the point when my temperature at this longitudinal end here becomes same as T naught. I can increase that. Yes or no?
Sir, but maximum dissipation will take place when the fin's temperature is TW.
So, okay.
The efficiency maximum.
No. So that is the theoretical thing. That is the theoretical. That's why I use that word theoretical. See, ultimately, see, if my temperature, see, my temperature will not remain TW here in the actual case. Why? Because my dissipation is continuously taking place as I'm moving along the longitudinal direction.
Sir, so if we keep the temperature of the end higher, then also we'll get higher efficiency.
I don't want it to keep it higher here because that is not the aim. My aim is all the heat should be dissipated outside, and that can happen only if the temperature here is lower. But for the calculation of the efficiency, only the theoretical maximum I'm calculating. Theoretical maximum. That's not what I am desiring. What I'm desiring is my temperature should become here as a ambient temperature. That's what I'm desiring. That means what? All the heat which is conducted here is getting dissipated till the end of the fin. Yes or no?
Okay, sir.
No, still not clear.
Still not. Got it.
That confidence is lacking. Is it?
Yes, sir, a bit. Like I have to think about it.
Okay, I will quickly try to explain again. When I am having this extended surface, what is my objective? My objective is to dissipate the maximum heat possible. Do you agree? Yes or no?
Yes, sir.
Now you may ask me, then if I increase the length of this fin to infinity, let's say, if I increase the length of this fin infinity, then my heat transfer area increases by infinity, isn't it? Do you agree?
Yes, sir.
But how long I can go maximum? Actually, how long I can go? Till my temperature at this end becomes T naught. Isn't it? Do you agree with this?
Yes, sir.
And that is the maximum length you can have, isn't it? If you are increasing your length beyond that, then you are only wasting money on some metal part, isn't it? Do you agree?
Yes, sir.
Isn't it? So that means the length of the fin should be maximum when my maximum till the point where my temperature becomes T naught. My longitudinal temperature here becomes T naught because temperature is going to decrease as I move along the longitudinal direction. That's what is going to happen because there's a continuous heat dissipation taking place as you move along, isn't it? So whatever heat I have added here, some will get dissipated here, remaining will get dissipated here, and that goes all the way along here. So eventually you will see that there is no heat remaining here, isn't it? That means the temperature here is going to become ambient temperature. Do you agree?
Yes, sir.
So what I am saying here is I will increase the length of this fin till the point where my temperature T here becomes the ambient temperature. That's what I'm saying. Now it makes sense. Does it make sense now?
Yes, sir. Yes, sir.
In that case, what will be my second boundary condition? The second boundary condition which I have used here, this will be 0, isn't it? When I reach x equals to L, there is no dissipation of the heat, isn't it?
Yes, sir.
With this assumption, then, you know, entire thing gets simplified. So at x equals to L minus k dt by dx equals to 0. In fact, this derivation you will see in several books rather than the generalized derivation I have given initially. So with this derivation, what you are going to get is the temperature distribution. You will get a very simplified expression, unlike the temperature distribution equation, which we have got a complex temperature distribution equation like this. You are going to get a very simple expression as cos hyperbolic L minus x divided by cos hyperbolic zeta L. That's it. All right. Is it clear to everyone? So you can solve the same expression here. This you can solve with the assumption that this is 0. This is 0, so you can put 0 here. Then find out C2. Back substitute C2 and C1 in this equation. And then again calculate everything. You will get T minus T naught divided by TW minus T naught is given as cos hyperbolic zeta L minus x divided by cos hyperbolic zeta L. These terms will become 0. These terms are going to vanish. Okay. Is it clear? Yes or no?
Yes, sir.
Now again, let's calculate the efficiency. What will be the theoretical, what will be the heat transfer? Total heat transfer will be BW minus K dt by dx. That again at x equals to 0. So we will get from this equation itself BW K zeta TW minus T naught sine hyperbolic zeta L by cos zeta L, because we can differentiate this equation with respect to x and we can put it in this equation. We will get this, and this cos hyperbolic zeta L is a constant term, so you have to only differentiate this numerator. So that will be sine hyperbolic zeta L and minus sign will be there. That minus sign will get cancelled out with this, isn't it? And this TW minus T naught will come out on this right hand side here. So that's why we are getting BW K zeta TW minus T naught sine hyperbolic zeta L by cos hyperbolic zeta L. Now what will be the maximum? Theoretical maximum. Theoretical maximum will be PL is going to be the area, isn't it? PL is going to be the area, but PL. So remember, in the earlier case, PL plus BW we have taken. PL plus BW we have taken earlier case. Here we don't need to take BW because now we are assuming that when I am reaching to this end, there is no heat transfer taking place here. So this area, even though this area is there, but it's not contributing in the heat transfer at all. So only PL is required. Do you agree? Isn't it? Where I am saying this assumption is there that there is no heat flux when I'm reaching to the x equals to L. That means that area is not at all important to me. BW. Do you agree?
Sir. Sir, in the initial derivation, the complex one, then also we had assumed that the width was very small, but then also we considered the area, the small area, but this time we are not considering it. I mean, why? Because then also the conduction was not taking place in the vertical.
No, here conduction is taking place when we are taking the vertical maximum. Okay, when we are taking the theoretical maximum, when we are calculating, we are taking the convection taking place from this end, isn't it? So convection from all the surfaces. So there will be this surface L, this surface B, this W, and there will be BW also here, isn't it?
Yes, sir. Okay, sir. We did not consider the conduction in the vertical.
Convection we have not considered.
Convection we have taken.
Okay, sir. So yes, that's why the maximum we have calculated based on this.
Yes,
when
sir.
we are calculating the theoretical maximum. But in the other case, even when we are calculating the theoretical maximum, this surface is not contributing in the heat transfer at all. Because what we are assuming in the simplified case that by the time I reach to this end, my temperature is already becoming T naught. So that means this area is not at all contributing in the convective heat transfer. Do you all agree? Isn't it?
Yes, sir.
That's why this BW which I have included in the complex case here, I am not including here. Here directly PL into H delta T I am going to have, and that delta T will be TW minus T naught. So that TW minus T naught get cancelled out. So finally, the expression which I am going to get is tan hyperbolic zeta L by zeta L. So this is the very simplified equation. So remember, both these simplified equations are with this assumption. At x equals to L, my heat flux becomes 0. All right. Again, here zeta is what? Zeta we have defined as pH by kBW earlier, isn't it? Zeta square is defined as pH by kBW. Now, in this case, we can say that, so see, in this case, we can say that this width is very small, isn't it? So in that case, P will be just 2B. So zeta square will be given as 2H by kW directly. All right. These are the simplifications. All right.
Yes, sir.
Okay. Okay. So let's move to the next interesting case. Now, what we are saying here is a critical insulation thickness. Okay. So now, okay, let's assume that there is a pipe. There is a pipe through which the steam is flowing. Let's say this is the pipe from which the steam is flowing. And clearly, I don't want it to lose the heat from the steam. That's why I will add a insulation above the pipe, isn't it? To avoid the heat transfer, isn't it? Correct. And then outside there is a ambient temperature. Is it correct? Yes or no? So the system is clear. So there is a pipe through which the hot steam is flowing. My objective definitely is to avoid the dissipation of the heat to the ambient, because I wanted to keep the quality of the steam intact. That I can do only if I eliminate the heat dissipation to the ambient. So that means this pipe, steam pipe, I will be insulating outside. So this shaded area is nothing but the insulation of the pipe. Okay, isn't it? And outside of this insulation, there will be ambient temperature. So do you all agree? Is the system is clear to everyone? Hello?
Yes, sir.
Now, as I'm saying that the steam is flowing with a very high rate, steam is flowing with some velocity here, and because of high temperature, or maybe liquid is flowing through this. So because of that, the heat transfer coefficient here, because of turbulence or something, the heat transfer coefficient here is very high. Okay. So convective resistance inside the pipe we can neglect, isn't it? Convective resistance where here we can neglect. Okay, but there is a conduction resistance because of this insulation which is there outside this pipe, and then there is a convective resistance from this insulation surface to the ambient outside here. Do you all agree? So inside temperature here is Ti, outside temperature is T naught. The radius, the pipe, inside pipe radius is Ri, but the radius with including the insulation is R naught, but the thickness of the pipe, we are assuming that thickness of this metal pipe, we are assuming that is a very small, and the conductive resistance through this metal pipe here is negligible. That's what we are assuming. Is it clear to everyone, the system? Yes or no? Still not clear? Say no if it is not clear. Hello? Hello? Am I audible? Hello?
Yes, sir, you are audible.
So is the system clear to everyone or not clear? Please say
Yes,
so. If
sir,
something
it's
is not clear, please say so. Not clear? Hello? It is not clear? Okay, all right. What I'm trying to say here is I am having a pipe, metal pipe.
Sir, your slides are not visible.
My slides are not visible now, or just now, or
so just now.
okay. Is it visible now?
Yes, sir.
So what I'm saying is I am having a pipe, metal pipe through which the steam is flowing. Clearly, I don't want it to have a heat dissipation from the steam to the ambient. So this metal pipe, I will apply insulation above it, isn't it? To avoid the heat dissipation to the surrounding so that the quality of the steam remain intact. Again, the steam is flowing with high velocity here. So the heat transfer coefficient inside this pipe we can consider as a very high. So heat transfer coefficient HI is very high, means this resistance is negligible here. Again, the metal resistance will be negligible because the conductivity of the metal is very high, but there will be a resistance corresponding to the insulation. So this insulation I have shown here by a shaded area. So this shaded area is nothing but the insulation. Again, the thickness of the pipe I am assuming very small, so that I am not at all accounting. So you can consider that is very small. So the R0 is nothing but the radius accounting the insulation. Okay, and again from this insulation surface there will be a heat dissipation to the ambient. So ambient temperature is T0 and the heat transfer coefficient here will be H0. Now why we are studying this? Why we are studying this? So this type of situation you will see regularly in process industry, and in this, as you increase the amount of insulation, so see, typically what we think is more the insulation we add over the pipe, my heat dissipation to the surface is going to decrease. That is what we anticipate, isn't it? But it's not going to happen. What happens is initially, as I increase the thickness of the insulation, thickness, what happens is the Q increases instead of decreasing. Why? Because as I increase the insulation thickness here, what you can see that the outside surface area, which is responsible for the convective heat transfer, that convective heat transfer area increases, and because of that the convection, the contribution of the convection in the heat transfer increases. Okay, but as further we increase the thickness of the insulation, you will see that the heat transfer first increases and then it start decreasing. So definitely whenever we wanted to apply some insulation over such pipe or such equipment, we have to first find out the critical insulation thickness. So your insulation thickness should be always above this critical insulation thickness. Otherwise, you end up with having more heat loss than saving the heat loss. Do you all agree? Yes or no?
Yes, sir.
Yes, sir.
So can you please explain why does the heat flow increases with insulation?
So see, here heat flow depends. In this case, the heat flow depends on what? It depends on the conductive resistance through this insulation. So conductive resistance is going to decrease as your thickness of the insulation increases. Do you agree? So conductive resistance is going to decrease because the thickness of the insulation increases. But as the thickness of the insulation increases, what will happen? This outside radius R0, this is going to increase. Outside radius R0 increase means what? The outside surface area, circumferential surface area from which your convection is taking place. Remember, in the convection, either you increase H or either you increase A. So here you are increasing the heat transfer area, outside heat transfer area, by increasing this R0.
Okay.
So your convective heat transfer is increasing. Even though your conduction is decreasing, but your convection is increasing because of that. And the resultant is initially your heat transfer is going to increase. And then if you start increasing the insulation thickness, it will start decreasing. So definitely your insulation thickness should always be above the critical insulation thickness. Does it make sense to everyone?
Yes, sir.
Okay, so that is what we have. Okay, so now let's look at this pipe flow here. So we can write down the heat transfer equation here. Q will be given by what? Delta T, and the conductive resistance will be given by what? Ln R0 by Ri divided by 2 pi Lk, isn't it? And what will be the convective resistance outside here? Remember, inside convective resistance, we are assuming negligible because HI is very high. But this H0 will have a significant value because it's a more rate limiting transfer. This resistance will be the rate limiting resistance, isn't it? So that will be given as 1 by H0 A0, isn't it? Correct? Yes or no?
Yes, sir. Yes, sir.
Again, if I multiply this 2 pi L here, we get R0 here, isn't it? H0 R0. Now I wanted to find out the insulation thickness. So what will be the insulation thickness? Insulation thickness will be what? R0 minus Ri. Do you all agree? Insulation thickness here will be R0 minus Ri. And this R0 is a variable because as I increase more insulation, more will be R0. But this Ri is fixed. Ri is the pipe diameter, isn't it? That is fixed. Do you all agree? Yes or no?
Yes, sir.
So I wanted to find out the value of R0 at which I am getting this maximum for Q. Yes or no? Does it make sense?
Yes, sir.
So that means what I will do? I will differentiate this dq by dr0 and equate to 0. If I do that, dq by dr0 and equate to 0, what I'm going to get is 1 upon kr0 minus 1 upon h0 r0 square equals to 0. So what you are going to get is r0 critical. R0 critical you are going to get is k by h0. K by h0. Again, if you differentiate this equation twice, you will get a negative term, isn't it? Negative term, that means whatever this R0 critical you have obtained is corresponding to the maxima. Okay. So now this K naught, K divided by H. K is nothing but here the insulation thermal conductivity divided by H naught is nothing but the heat transfer coefficient outside here. So this is nothing but the critical insulation radius. This is nothing but the critical insulation radius. But what will be critical insulation thickness? R0 critical minus Ri. So if I subtract Ri from this expression, then it will be a critical insulation thickness. Do you agree? Do you agree with me?
Yes, sir.
Again, this I have calculated for the cylindrical geometry, but you can calculate this for a spherical geometry. For spherical geometry also you can obtain a similar expression. Is it clear to everyone what we are doing?
Yes, sir.
Now another thing is that not always you will get the critical insulation. Sometimes let's say if you calculate K by H0 and that comes out to be less than Ri. Less than Ri. What it means? If it is less than Ri, that means that there the critical insulation thickness does not exist for such cases. That's what it means. Is it clear to everyone? Hello?
Does not exist means?
Does not exist. So see, it may possible that your thermal conductivity of your insulation is such that it is, let's say, small. It's not very high, let's say. Okay. And if you divide and if your heat transfer coefficient H0 is very high, let's say thermal conductivity K is small and H0 is very high. In that case, K by H0 can come less than Ri also. Remember, this R0 critical is the value you have calculated from this, and this should be this. I am saying that I should maintain this R0 beyond this R0 critical. That's what I'm saying. But I can calculate R0 critical directly from K by K and H0, and that may come out to be less than Ri. Sometimes depending on what value of K and what value of H I am having. Do you agree?
Yes, sir.
So that means what? In such cases, the critical insulation thickness does not exist. So what it means is in such cases you will get continuously decreasing Q profile as your insulation thickness increases instead of going top and then decreasing. It's not. Is it clear to everyone?
Yes, sir.
Okay, all right. So so far we were talking about the critical insulation thickness. There is another terminology which is called as economic or optimum insulation thickness. So see, so far we are saying that if I increase the insulation thickness beyond this critical value, my rate of heat transfer is going to decrease. So that is what I'm desiring. I don't want heat to be dissipated to the ambient from my fluid here inside the pipe, isn't it? Correct. That is what my objective is. So more heat is lost from this steam, more is the cost incurred to you, isn't it? Because the heat dissipated means that is the wastage of the steam in a way, isn't it? Yes or no?
Yes,
Do you all agree or not? If I am having more heat dissipated to ambient, that means this steam here inside the pipe is going to cool down. That means the quality of the steam is going to decrease. So when the steam is going to cool down, that means it will be condensing somewhere, isn't it? So I will lose the amount of steam by that. So that is a loss to me in terms of monetary basis. Do you agree?
Yes, sir.
Yes.
And again, if I increase the insulation thickness, my resistance is decreasing, my heat transfer is decreasing, but there is a cost required for this insulation. I cannot increase the insulation thickness to infinity, isn't it? More the insulation I am putting, more the cost will be incurred in terms of insulation cost. Do you agree? Isn't it? So I cannot put the, I cannot increase this insulation thickness to a very large value because the insulation will also cost me something. So I wanted to look at this entire problem in an economics point of view, isn't it? I wanted to use the thickness of insulation such that my cost minimizes. Does it make sense?
Yes, sir.
Isn't it? So that's what is called as the economic or optimum insulation thickness. So there are two opposing factors. So heat loss is reduced. So if we increase the insulation above the critical thickness, the heat loss is reduced. The cost of the energy lost is decreased. Okay, cost of the energy lost is decreased. But the cost of the insulation is increasing. Higher cost will be there for insulation. So there exists an economic or optimum insulation thickness for which the sum of the insulation cost and the cost of heat loss is minimum. All right. And there are different factors are there while calculating this. So what are the factors? So first is the insulation you are going to buy today, and that insulation is going to last. It is going to last for few years, maybe 10 years, 20 years, isn't it? So you are not going to replace your insulation every year, isn't it? You will buy today, but then it will last for maybe 10 years or 20 years, isn't it? Depending on the quality of the insulation you are using. Isn't it? So there is a fixed cost of insulation you are going to have in year number 1, isn't it? Then variable cost like maintenance cost will be there, isn't it? Also service life of the insulation. So how much is the life of the insulation is important. So this whatever the cost you are incurring for the insulation, whether that is spanned over 5 years, 10 years, that is important, isn't it? Also depreciation. Okay. So whatever, okay. So here the depreciation in the sense that this insulation which you are adding here, whether its value is decreasing over the year, that is called like a depreciation, and taxes. Okay, so all these are the factors involved while calculating the economic or optimum insulation thickness. Again, let's look at the same system. H0 is the film coefficient at the outer surface here. K is the thermal conductivity of the insulation. C is the cost of insulation, let's say, capital C. And CH is the cost of heat energy, rupees per kilocalorie, let's say. Okay. Again, thermal conductivity is kilocalorie per hour per meter degree Celsius. Heat transfer coefficient H0 is kilocalorie per hour per meter square degree Celsius. I is the interest rate, that is per year. N is the number of insulation line, number of years. T0 is the ambient temperature in degrees Celsius, and Ti is the pipe wall temperature in degrees Celsius. Again, we are assuming that the convective resistance inside here, inside the pipe is negligible. So Hi is very high. Is it clear? Is the problem is clear?
Yes, sir.
So now in this case, the overall heat transfer coefficient based on the inside surface area, overall heat transfer coefficient based on the inside surface area, we can write down this equation. This is what we have seen, isn't it? Ui will be given as Ri ln R naught by Ri and K divided by K plus Ri by H naught R naught. That is what you are going to get the overall heat transfer coefficient inside based on the inside surface area. Again, the unit here is kilocalorie per hour per meter square degree Celsius. Okay. Now this Ui into the inside surface area 2 pi RIL, 2 pi RIL, that is the inside surface area, multiplied by this overall heat transfer coefficient based on the inside surface area, multiplied by delta T will be the amount of heat lost, isn't it? So Q is given as UA delta T, but again we wanted to calculate this Q over the year. So we wanted to calculate this Q in an annual basis. Remember here U is kilocalorie per hour. So how many hours we are having in 20 in a day? 24 hours are there, and we are assuming that there are 300 working days. So 24 into 300, this will be the amount of heat lost over the year. Is it clear? Is it clear to everyone?
Yes, sir.
Now this much is the amount of heat lost over the year, and this heat lost, if I multiply it to a cost factor CS, so that will be the amount lost over the year. This will be the amount lost over the year, isn't it? Correct. So this amount of lost over the year you will be paying every year, isn't it? And you wanted to calculate your entire balance over the service life of the insulation. So that means whatever you are paying every year will be divided by interest rate and all. So overall, over the n years, how much amount you are going to pay, or you are going to pay, that will be given as P1. So P1 will be QCH divided by 1 plus I raised to the power J, where I is the interest rate you are having, and this J will be 1 to N. Okay, so you are calculating how much amount you are going to pay over the N years for the heat loss. Is it clear? Yes or no?
Yes, sir.
So you are calculating how much amount you are going to pay as a cost for this heat loss over the service life of the insulation. So this way P1 will be the total amount you are going to pay over the service life of the insulation. Now volume of the insulation applied will be what? Pi R naught square minus pi Ri square into this entire thing by L, isn't it? So R naught square minus Ri square, that will be the amount of insulation you are adding, isn't it? Multiplied by pi L will give the total volume of the insulation you are going to apply. So in general, the insulation material is purchased in volume. Okay, so that's why we are calculating how much will be the amount of volume required for a particular thickness of the insulation over the pipe. Is it clear?
Yes, sir.
And this volume of the insulation, then we are multiplying by a cost factor. So cost factor of the insulation, you can see per meter cube is given. Cost of the insulation is per meter cube is given. Okay, so that you are multiplying. So P2 is the cost of the insulation, isn't it? P2 is the cost of the insulation. Now what you are trying to do, this P1 and P2 both are the cost. You wanted to minimize this, both these costs. So P1 plus P2 is the total cost PT. So total cost is given by this first factor QCH summation over J equals to 1 to N, QCH divided by 1 plus I raised to the power J plus pi this second factor as it is, isn't it? And then again here Q we are putting this original expression, isn't it? Q we are putting, and in this original expression again we are putting U by this particular expression. So this is the final expression we are getting. Okay, and this expression we wanted to minimize with respect to what? We wanted to minimize with respect to the insulation radius, isn't it? R naught. So this PT divide this expression, what we are going to do is dPT by dR naught That is what we are going to equate to 0. And based on that, we are going to find out the optimum value of R naught. So clearly, this particular equation looks very complicated, isn't it? So you can use some numerical method to solve this and find out dpt by dr naught equals to 0 and find out the optimum value of R naught. And that R naught represents the economic or optimum insulation thickness. Optimum insulation radius, and optimum insulation radius minus Ri will be the optimum insulation thickness. Do you agree?
Yes, sir.
So this is what we have done. dpt by dr naught we are getting. So here you can see that this is the economic insulation thickness I am going to have. So here you can see there are two costs. P1 is the cost of the heat lost, isn't it? So as you increase the insulation thickness, this P1 is going to decrease. But as you increase the insulation thickness, your insulation cost is going to increase, which is shown by this red dotted line. So there exists a optimum point where the summation of both these P1 and P2 is minimum. So this is something called as a economic insulation thickness. Clear to everyone? Hello?
Yes, sir.
Yes, sir.
Okay, so we stop here. And unless you have any question to ask, is there any question? Hello? Hello, is there any question? So if no question, let us stop here. See you all on Wednesday for a tutorial. All right.
Thank you, sir.
Thank you,
Thank you,
sir.
everyone.
Thank you.
Thank you, everyone, for joining. At least those who are joining, they deserve a big thank you from my side. Thank you for coming. Okay.
Sir.